Hi, I'm Ryan Baker and this is Big Day in Education. In this lecture, we're going to continue our discussion of relationship mining by discussing a way to go beyond just correlation to getting to actual causal relationships, causal data mining. So I want to start this lecture by saying I'm not actually an expert in causal data mining. And this is a method that's easy to mess up, so I wanted to make sure to get some expert advice. And I got that expert advice from Steve Fanksally at Carnegie Learning. So these slides are developed in partnership with him, but if there's any errors, it's probably me. So let's thank Steve and let's move on. So causal data mining. It's distinct from prediction or correlation mining. The goal isn't to figure out what predicts X, or to figure out what's correlated with X, but instead to figure out causal relationships in the data. In other words, A causes B. I made this video, you learned. Some examples from Richard Shyness, who's a big leader in causal data mining and educational data mining. What features of student behavior actually cause learning? Not just what's correlated with it, but what's actually causal. What will happen when we make everyone take a reading quiz before each class? What will happen when we program our tutor to intervene to give hints after an error? In causal data mining, we use graphs to represent causal structure. And these are usually directed graphs, which means they have arrows on the links, without cycles, which means you can't have chains of causation. Now in the real world, you can have chains of causation, but boy, it makes it hard to model it. Typically when people want to look at chains of causation, they look at it as non-cycles, directed links, but over time. And by the way, this may seem familiar if you're remembering the Bayes network lecture from week 4. It's the same mathematical framework. Nodes represent variables, and directed edges between them represent causal relationships. And the algorithms available for causal data mining infer causal graphs that explain dependencies in the observed data. And I want to point out we say classes of because usually from the observed data alone, we can't infer a unique causal graph. Causal data mining to be effective relies upon additional information, which I'll talk about a little later. So finding causal structure. One thing people often say is, well, why don't you just do a randomized control trial? That'll make it easy. The answer is that some experiments are impossible, or they're too expensive to run, or they're actually unethical. Sometimes you can find data sets from the real world that allow you to ask questions that you just can't really ask without it. Can you determine this from purely correlational data? Sprites, Gleimer, and Shyness say, sometimes yes you can. You can find causal structure that emerges from data, even if it's not obvious from the patterns of covariance. Let's give a quick example. Is repeatedly retrying quizzes harmful? So let's say I'm allowing students in my course to retry their quizzes 3, 5, no, 100 times. Is this going to be good for their learning? Well, let's say, does repeatedly retrying quizzes cause decreased learning? That's really the question when we want to say causal. Suppose that an investigator notices that repeatedly retrying quizzes and the final exam score are negatively associated, in other words, correlated. So the students who retry quizzes a lot get worse scores in the exam. Can we simply conclude that repeatedly retrying quizzes is bad for you and we should turn it to only have one opportunity? Maybe. Because a direct causal relationship could explain this correlation. Retrying quizzes causes a lower exam score. But on the other hand, the correlation between retrying quizzes and exams might arise from a common cause. It might be that students who know less to begin with are more likely to retry the quiz, and they're also likely to do worse in the course exam. And the retrying quiz there's no thing that goes between those two, actually. By the way, it could also be both. That's what this graph shows. Maybe pretest influences both retrying the quiz and the exam, but retrying the quiz even beyond that influences the exam. Also possible. So suppose that when we control for pretest, the correlation of retry quiz and exam disappears. In other words, the partial correlation of these two, retry quiz and exam, covariating out for pretest, is not significantly different than 0. Well, 3 causal graphs can explain this conditional independence equally well still. It might be that retrying quizzes causes lower pretest, which causes lower exam. It might be that the pretest causes lower exam and more retry quiz. Or it might be that doing well on the exam makes your pretest lower, which in turn makes your retry quizzes more. Each of these causal graphs can explain things equally well. What do we do? Well, if we know the pretest occurred before retrying the quiz and the exam, then we know that retrying the quiz can't change the pretest, and the exam can't change the pretest. And that allows us to hone down which of these possible causal models is actually the correct one. So the big idea, infer classes of graphs that can represent the full pattern of dependencies and independencies among the measured variables. The key package for doing this is Tetrad, which is available on the web. It's a neat package. Tetrad implements multiple algorithms for inferring causal structure from data, and different algorithms are applicable given particular assumptions. These assumptions guide the algorithm choice. For example, perhaps there are unmeasured common causes. Perhaps doing poorly on the quizzes and having to retry them, and doing poorly on the exam don't have anything to do with the student, but simply have to do with a terrible instructor who can't write assignments or exams. Another assumption we have to ask is, do we think the relationships between variables are linear? You'll want to use different algorithms depending on whether they're linear or not. And are the underlying dynamics of your causal model cyclic or cyclic? In other words, are there cycles in there where A influences B, which influences C, which in turn influences A, and you get a feedback loop, vicious or virtuous cycle, or is it all kind of going through time smoothly? And are the distribution of variables Gaussian or non-Gaussian? For a discussion of which algorithm is the right one to use for each of these cases, I'd like to refer you to the Tetrad user guide, which can go into much more detail on this than my lecture can. For the math and assumptions, it's hairy, it's hard work, it's good slogan. This is a good paper to read, and this is a good book to read. I read the book first, I read the paper second. That'd be my recommended order. Let's look at some examples in EDM. Causal data mining has actually become pretty popular in EDM the last couple of years. One example is from Steve Fanksally. Hey, he provided some slides and some advice. We'll go over his example. What you can see is that gaming the system is influenced by pretest score. If you have a better pretest, you game the system less. If you have better pretest, you also work less than the tutor. Off-task behavior is not linked to pretest score. However, both off-task behavior and how much you game the system influence how much feedback you get, and how much feedback you get is associated with doing worse in the final exam. This example uses an algorithm that allows for unmeasured common causes of measured variables. In other words, pretest score to total steps, the negative correlation between these two, can signify, 1, that pretest score is a cause of total steps, but 2, they share a common cause, or 3, both. So the important thing is, when you're looking at this kind of graph, or writing about it, make sure that you're very clear that the pretest score and total steps might be coming from the same common cause, as much as pretest score may be influencing total steps. This is an example of, you don't just want to publish a graph, you actually want to explain what the graph means, and to do that you gotta understand what you're doing. Causal data mining, even more than other methods in this class, is not just a method you should use if you're clueless. Learn what you're doing and make sure to do it right, because you can do some silly things. Let's look at another example, Rao and Shyness. In this one, they were looking at the effects of multiple representations and students' self-explanation on learning of fractions. And you can see that whether or not the system had multiple representations, and whether or not the system promoted self-explanation, influenced how many hints and errors the student saw, which in turn influenced the student's post-test and their delayed post-test. Another example comes from Devon Rai and Joe Beck, who compare the results when you do an unconstrained model and a constrained model using domain knowledge. When you use an unconstrained model to try to study the relationship between students' self-report of their experience with a tutoring system, their performance in the tutoring system, and pre-test and post-test given before and after the tutoring system, they found that students who like math and don't find the tutor confusing get more problems right. And then, getting more problems right causes them to do better on the pre-test they took before using the tutor. Some of you may have noticed an issue. If they take the pre-test before they use the tutor, then their performance in the tutor can't possibly cause their pre-test. And this is what happens when you use unconstrained models, and this is why you have to do what Devon and Joe did and actually pay attention to using the right model. They then showed that if you do it right, you get a more reasonable result. So their solution? Use domain knowledge to constrain your search. The future can't cause the past. And this is similar to pretest being prior to retry quiz and exam. The corrected model, when set up correctly, actually had a much more reasonable pattern. Gender caused attitudes, which caused performance in the tutor, which in turn caused other performance in the tutor, and post-test scores. So it's important to use causal modeling algorithms correctly. If you don't, you can come up with some really silly stuff. Which assumptions are reasonable? For example, the future can't cause the past, except in movies. Another important consideration, are variables good proxies for what we intend to study, especially if they're latent variables? Suppose pretest isn't an appropriate measure of prior knowledge. Pretest then might not screen off retry quiz and exam, so we might still think that retry quiz causes the decreased learning on the exam because our pretest didn't actually measure the fact that both were caused by prior knowledge. So it's important here, as with anywhere, to have good meaningful variables. So causal modeling is a powerful tool, but it needs to be used carefully. You can really mess it up. Now, another type of causal inference, which is worth noting, is making causal inferences from quasi-experimental data. For instance, figure out ways to treat a quasi-experiment as if it were an experiment. Now, this is a very big area in its own right, and it's more statistics than machine learning data mining, so I won't discuss it in detail. So this concludes our lecture on causal data mining. In the next lecture, we'll talk about association row mining. I'm Ryan Baker. This is Big Day in Education. Thank you very much.